So what you can see here is the result from example 3 that's been worked out. You should have gotten that 13/6, 3 halves is your critical point. That is a relative min. If you need to pause the video to find any mistakes that you may have made, please feel free to do so. The next part that we're going to discuss are going to be applications involving optimization. So this means we want to find either the biggest or the smallest value of the function and when this happens. Typically, profit wants to be maximized, whereas something like cost is going to be minimized. It's all about what makes sense in that context. So in this example, we are given the monthly profit function in dollars that a company makes when they produce and sell its speaker systems, given by the function you see there. X is the quantity of standard systems. I'm going to underline that. X is the quantity of standard systems and is produced and sold each month. Y is the quantity of deluxe systems that are produced and sold each month. So we need to understand the difference between X and Y. Find the maximum profit and verify using the d-test that your answer gives you a maximum. Great. So first thing we have to do is find the partial derivative of the profit function with respect to X. So y is a constant, then differentiate with respect to y, so x is a constant. And then while we're at it, finding derivatives, let's just go ahead and figure out our second partial derivatives. We're going to eventually need these when we find the d-test formula. Okay, so now we're ready to find our critical points. We're going to find the critical points by setting your first partial derivatives each equal to 0, solving the resulting system of equations. All right, these look kind of nasty with all the decimals. We're going to do a quick trick to get rid of all of our decimals by multiplying each equation by 100. Multiplying through by 100 is going to eliminate our decimals wherever they would appear. All right, this is what you get as a result. So no more decimals, but now we have some pretty big numbers. We're going to look at each of the numbers in each equation and decide if we can divide out a common factor. Now the first equation looks like I can divide out by a common factor of 25. That would be useful. The second equation I could divide out also by 25. So that's going to reduce our numbers a little bit for us. You could have done both of these steps in the same instead of multiplying by 100 and dividing by 25. You could have just multiplied by 4 and both things would have accomplished the same result in one step instead of two. But we didn't do it that way. Now, I want you to notice that the equations are not in the same order. In other words, the first equation has x, then y, whereas the bottom equation has y and then x. So when I rewrite my equations, I am going to rearrange everything. So the x's are first, the y's come next, and then the constants go to the other side of the equal sign. I think I have one too many zeros on that. That looks better. Okay, so this looks like it could be right. Hopefully I didn't make any mistakes, but next we want to try to solve the equations however you like. And so you could use substitution again, or you could use the addition, or otherwise known as the elimination method, which that's the way I'm going to choose to solve this right now. So I'm going to multiply it through the bottom equation by -2. What that's going to do is it's going to give me a positive 2x in that first location. That should be positive 800. And then when I add like terms together from top to bottom, the x cancels out. So just remember that you need to add like terms for this to work. Okay, so I end up getting y equals 64. That seems reasonable. If y is equal to 64, what does x need to be? Well, that's a good question. Remember that, let's see, let's find a good relationship between x and y. I don't know, this one looks good. I'm going to plug in the value of 64 for x. I'm going to compute what, for y rather, and I'm going to compute what x needs to be. So negative 2x minus 64 equals negative 480 should be x equals, let's see, so you add the 64 and then divide by -2 and you get 208. X refers to how many standard system speakers we want to sell, produce and sell, and Y represents how many deluxe systems, which is going to be 64 in this case. Now we're going to verify that your critical point, 208, 64, does indeed give you the maximum, is a relative maximum to give you that maximum profit. So in order to verify this, we need to come up with your d-test formula. So let's see if I can separate this a little bit. So your d-test, d of x, y, that's going to be negative 0.5 times negative 0.75 minus negative 0.25 squared. And this is going to be a positive 0.3125. Great, that's bigger than 0. So that means I have to go to the next idea, which is fxx. The second partial with respect to x, rather, instead of f, I guess I should be writing p, since we're talking profit. Okay, so the second partial of p with respect to x both times is up there at negative 0.5. That is less than 0. That means that your graph is concave down, which means that your point that you found is a max. Next up, we have a concert venue that produces 2 kinds of souvenir shirts. The total cost of producing X of style A shirts and Y of style B shirts is given by the formula you see in thousands of dollars. Don't forget that. Sometimes I forget the units. Thousands of dollars. Using the method of calculus that we've just discussed, find the total number of each style of shirt that should be produced in order to minimize the cost. I want to minimize the cost this time. What's the minimum cost? And verify using that d-test formula that we've discussed. So we want to find the partial of c with respect to x, and we are going to get 8x minus 6y minus 200. Find the partial with respect to y, we should get negative 6x plus 6y plus 18. And find the second partials while we're at it. All right, so we've got that for later. Next, we are going to find the critical point by setting those two partial, the first partials equal to 0 and solving simultaneously. So how about 8x minus 6y minus 200 equals 0, along with negative 6x plus 6y plus 18 equals 0. I'm going to rearrange each one. I'm going to get the constant to the other side. So it's equal to 200 on the first, and it's equal to negative 18 on the second. Now, I don't know if you noticed this, but I don't have to do a whole lot of work here. I can solve directly where it is because the y terms will cancel out if I simply just add like terms together from top to bottom. That's going to give you 2x equals 172. And if I divide by 2, what is x? X is 91, I believe. So if x is 91, I need to verify that. Hold on. 172 divided by 2, 86. Where did I get 91 from? So sorry. Okay, stop doing that. 86. That's not 172, is it? Nope. It should be 182. 182. All right, let's fix this answer. So 91. Finally got there. X should be 91. So if I need to make 91 of style A shirts, let's figure out what Y should be. I'm going to plug X equals 91 back into any of my equations here that involve X and Y. Let's use, how about this one? Okay, so I'm going to plug X equals 91 right there for X, 91 minus 6Y equals 200, and solve for Y. Let's see, 200. 88. Gonna make 88 of style B shirts. In order to minimize my cost, let's make sure that I got the minimum with my critical point. 91, 88 is my critical point. Verify that it is a relative minimum. So we've got D. D is equal to 8 times 6 minus quantity negative 6 squared. 48 minus 36. That's 12. That's positive. So far, so good. Now find F, not F, C. Find CXX. CXX was 8. Remember we found that earlier? That's positive. Since they're both positive, we have just verified that the critical point, 91, 88, is a relative minimum. There you go.